Today's lesson is on implicit differentiation. We'll be looking at implicitly defined functions, lenses, tangents, and normal lines, derivatives of higher order, and rational powers of differential functions. Our basic rule is we're going to look for and solve for dy dx in terms of x. In order to do this, we'll have to divide and solve implicitly, which means that every time you see a y, you're going to take a derivative as if it's an x, and then whenever you take a derivative with respect to y, we're going to tack on dy dx. Here's an example of a function, x cubed plus y cubed minus 9xy equals 0. We have ellipse and hyperbole and different types of functions that are enclosed where we will be able to find their derivatives. 4 steps: differentiate both sides of the equation with respect to x, collect the terms on one side for dy dx's, factor out the dy dx, and then finally solve for dy dx. Here's an example. Our first example, y squared equals x. Solve for y squared like an x for the derivative. Derivative of y squared is 2y. The difference is, for this one, we're going to tack on dy dx. Derivative of x equals 1. Now I'm going to get dy dx by itself. To do that, I have to divide both sides by 2y. And that's our derivative. Dy dx equals 1 over 2y. Next example. Take the derivative. Derivative of 3y squared equals 6y. Dy dx, because it's a y, we always tack on dy dx when we take its derivative, plus derivative of 2y is 2, dy dx. Derivative of 5x is simply 5. We have both of the dy dx terms on the left side of the equation, so I'm going to factor out dy dx on the left side of the equation. Write down what's left, which is 6y plus 2. Then to get dy dx by itself, divide by 6y plus 2. So our derivative, dy dx, equals 5 divided by 6y plus 2. Next example, take the derivative on the left, would be 2. Because it's a y, tack on dy dx, equals 2x plus derivative of sine is cosine of y, tack on dy dx, because it has a y with it. Group the dy dx terms together. That would be this one and this one. So I'm going to bring the cosine to the left, 2 dy dx minus cosine of y dy dx equals 2x. Factor out dy dx on the left. 2 minus cosine y equals 2x. Divide by whatever's with the dy dx, 2 minus cosine y on both sides. And then we have our derivative dy dx. So here it is. One of the big applications is lenses. We've talked about lenses in class before. We can find an equation of a line normal to a surface at what's called a point of entry, and an equation of a tangent line as well. Implicitly defined functions are very common for finding tangents and normals of lenses. So here is an example of a picture of what it looks like. We have our tangent line right here, Normal line is here. Here's our lens. And here's the point of entry. And what these two lines determine is exactly that point where the tangent and normal line intersect. Here's an example. Find the normal and tangent to an ellipse. Find the derivative first. Derivative of this right here is 2x. On this piece we have to use the product rule because there are two different functions multiplied together. Minus, I'm going to bracket off the x times y, so I remember to distribute the negative to the whole thing when I'm done. U is x, dv is 1 dy dx, plus v is y, no derivative, so just write it, times derivative of x is 1, plus, now we do the next portion, 2y dy dx equals 0. Don't forget, derivative of 10 is 0. I'll distribute the negative inside of the parentheses. Next, we group the two terms with dy dx, that's this one and this one, together. Bring everything else, this and this piece, to the other side of the equation on the right. I'm left on the left side with negative x dy dx plus 2y dy dx. On the other side, negative 2x plus y. Factor out dy dx on the left. Negative x plus 2y is left. On the right, we have negative 2x plus y. Divide by negative x plus 2y on both sides. And here we have our derivative. Plug in the value to find the slope. Negative 1 for x, positive 1 for y. So we have negative 2 times negative 1 plus 1 divided by opposite of negative 1 is 1 plus 2 times 1, which equals 3 over 3. So our slope is 1. Now we can write our equation of our line tangent and our line normal. Our point was negative 1, 1. Slope was 1. Y minus the y value equals slope x minus the x value minus negative 1 plus a positive 1. So this is tangent. Normal line. Y minus 1, opposite reciprocal, negative 1, x plus 1. Now we have what we just saw in that earlier picture for the lens, an equation of a line tangent and an equation of a line normal. We could graph them to find their intersection points. Okay, second, derivatives. Find the derivative. Like before, derivative of y squared is 2y dy dx. Derivative on the right, 2x plus 2. Divide by 2y on both sides to get dy dx by itself. We have our first derivative. If you can take out the same factor or the same number for each and every term of the numerator and the denominator, we can do so to simplify the first derivative. I would recommend this because we're going to find a second derivative. Factor out a 2 from each of the terms, we get x plus 1 over y. Second derivative, we're going to have to use the quotient rule on the first derivative to get the second one. So So we'll use u over v. So we start with v, which is y, times derivative of x plus 1 is 1, minus u is x plus 1, times the derivative of y is 1, dy dx. Again, remember, you only tack on dy dx when you take a derivative with a y, all over v squared, which is y squared. This next step is different than what we normally do for the second derivative. We already know what dy dx is. We just found it up here. We're going to substitute and replace dy dx with what it equals. So we'll replace this right here. We get y minus x plus 1 times x plus 1 over y all over y squared. We can't leave a denominator over another denominator. I'm going to do some algebra next to finish solving this. I multiply to get a common denominator with this y right here, over here by y over y. So I get y squared over y minus, I'm going to treat this as two of the same, so I'm going to write it as x plus 1 quantity squared over y all over y squared. Now we can write this over one common denominator, y squared minus x plus 1 quantity squared all over the common denominator I just created of y. And instead of dividing by y squared this time, I'm going to use the idea from algebra of flip and multiply. So divided by y squared over 1 is the same as multiplying by 1 over y squared. Our answer, y squared minus x plus 1 squared all over y cubed. And that's our second derivative. So we can label it d squared y over dx squared. For second derivative equals. Here's just another example of a circle. First derivative, 2x plus 2y dy dx equals 0. Solve for dy dx. Again, we're going to use the quotient rule, u over v. We take v, which is y, times derivative of x is 1, minus, the whole thing here, by the way, the negative comes over here. U is x, derivative of y is 1, dy dx. Replace dy dx with negative x over y. Get a common denominator, so we multiply this by y over y. We get y squared plus x squared. And then all over y squared again, you flip and multiply, becomes over y cubed. The last thing, we have a power rule for rational powers of x. It works exactly the same as the other problems that we've been solving for with regular powers. The reason it's in this section is because we have roots. So remember that square root is a half power, cube root is 1/3 power, fourth root is 1/4 power. Also remember that the negative here means that if we rewrite it, we can bring it down to the denominator, it would still be positive. So this is the same as 1 over cosine x to the positive 1/4. Getting to our problem here, we do the same thing as before, so we need to bring down the power, leave what's inside the parentheses alone, subtract 1 from the power, times the derivative of what's inside, and that's it. The assignment was from section 3.7, problems 1 through 37, odds. And that's it for today.